Now, in this lecture, you'll find out the radius of a circle using two different methods. In the drawing, we have triangle ABC. Triangle ABC blocks this circle, or this circle is inscribed by triangle ABC. In addition, we know that this is angle ABC that is equals to 60 degrees in its size, and this angle ACB equals to 75 degrees in its size, and line segment BC or side BC of this triangle ABC equals to 2 units in its length, and our mission is to find out the radius of this circle. So we start with the first method, and from point C we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. So by doing this construction, we can deduce the right triangle BDC. So I copy the right triangle BDC in the new page and we will analyze it. So actually, this is the right triangle BDC that I copied from the original drawing. BC equals to 2 and angle BC equals to 60 degrees according to what is given as the question. This angle equals to 90 degrees according to our construction. So in the right triangle BDC, cosine 60 degrees equals to BD over BC. So I write it down. Cosine 60 degrees equals to BD over BC. Cosine 60 degrees is 1/2. So substitute cosine 60 degrees by 1/2. And it is equals to BD over BC, and BC is 2, so we substitute BC by 2, and finally we found out actually that 1/2 equals to BD over 2. Here we multiply this equation by 2, and finally we get that BD equals to 1 unit in its length. This line segment BD equals to 1 unit in its length. We will continue to focus on this right triangle BDC. In the this right triangle BDC, sinus 60 degrees equals to DC over BC. Okay. Sinus 60 degrees equals to DC over BC. Sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC. BC is 2. So in conclusion, we found out the square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally we get that DC equals to the square root of 3 units in its length. So, here, this equals to the square root of 3 units in its length. You can write down here that this side DC equals to the square root of 3 units in its length. So, in the right triangle DBC, the sum of the angles must be equal to 180 degrees. It's true in any triangle, and especially it is true in the right triangle DBC. So which angles we have inside this right triangle DBC? We have this angle that is equal to 90 degrees plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Plus the missing angle, in total they must be equal to 180 degrees. Therefore, this missing angle must be equal to 30 degrees. In order to complete the sum of the angles in this triangle DBC to 180 degrees, the missing angle here must be equal to 30 degrees. It is given us the question that the big angle ACB equals to 75 degrees in its size. The small angle BCD equals to 30 degrees in size. So the big angle minus the small angle must be equal to the missing angle, this is actually angle DCA. The big angle equals to 75 degrees, the small angle equals to 30 degrees. 75 degrees minus 30 degrees is 45 degrees. So the missing angle here equals to 45 degrees in its size. That is to say angle ACD equals to 45 degrees in its size. In the next step, I will copy the right triangle ACD in a new page and we will analyze this right triangle, triangle ACD. So actually, this is the right triangle ADC that I copied from the original domain. Side DC equals to square root of units according to what we have already found out. And angle ACD is the missing angle that is equal to 45 degrees in its size. So, here in this triangle ADC, the sum of the angles must be equal to 180 degrees. So which angles we have in this right triangle ADC? We have this angle that is 90 degrees, plus this angle that is 45 degrees. 90 degrees plus 45 degrees is 135 degrees. plus the missing angle, in total they must be equal to 180 degrees. So the missing angle here must be equal to 45 degrees in size. In order to complete the sum of the angles in this triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees in its size. So angle DAC equals to 45 degrees in its size. So in this right triangle ADC, those two angles are equal to each other. And we have the rule that in front of equal angles in the triangle there are equal sides. So those two sides that are located in front of those two equal angles must be equal to each other. That is to say, side AD must be equal to side DC. AD equals to DC according to the rule that I mentioned. But we already found out that DC equals to the square root of 3 units, so we can write in that DC equals to the square root of 3 units instead. And for this equation, AD equals to DC equals to the square root of 3 units. We derive that AD also equals to the square root of 3 units in its length. Side AD equals to the square root of 3 units in its length. You can write here that this 9 segment AD equals to the square root of 3 units in its length. We continue to focus on the right triangle ADC. According to the Pythagoras theorem, here by PT is the expression for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ADC, AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is also equal to 3, this is equal to 3 squared, DC squared is equal to 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, 3 plus 3, that is 6. AC squared equals to 6. Here we take a root out to this equation, and finally we get that AC equals to the square root of 6 units in its length. AC equals to the square root of 6 units in its length. We can write down in the original drawing that side AC of this triangle ABC equals to the square root of 6 units in its length. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by a triangle ABC, that could be any triangle, is equals to R, the radius R equals to the area of triangle ABC that blocks the circle, over S. S is the semi-perimeter of the same triangle ABC. And the semi-perimeter of any triangle equals to the perimeter over 2. The perimeter is the sum of its sides length, and if we divide the perimeter by 2, we get the semi-perimeter S. So in the drawing of this rule number 15, we have a circle that is described by this triangle ABC. And whenever you have a circle that is described by a triangle, then the radius of the circle will be equal to the area of the triangle that blocks the circle. In this case, it is the area of triangle ABC that could be any triangle. So it is the area of triangle ABC that blocks the circle over S, that is the semi-perimeter of the same triangle ABC. So we can actually implement rule number 15 in our drawing. We can implement rule number 15 whenever we have a circle that is described by a triangle. Here we have this circle that is described by triangle ABC, therefore we can implement it, rule number 15. We define the radius of this circle as R, so the radius R, according to rule number 15, the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again. According to rule number 15, the radius of this circle that is described by triangle ABC, the radius R, equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle is the base of the triangle times the height to the base over 2. We have to divide this area by the semi-perimeter S. So we will take the base of this triangle ABC as AB. So the height will be DC. Why? The height DC creates 90 degrees with the base AB. So repeat again. The base of triangle ABC is AB, the height to the base is DC, divided by 2. This is the area of triangle ABC. We have to divide the area by S. So here, side AB of this triangle ABC, in total it is equal to the square root of 3 plus 1, square root of 3 plus 1. Again, the length of side AB is square root of 3 plus 1 unit. So we substitute AB by square root of 3 plus 1 times DC. From the domain, you can see that DC equals to square root of 3 units in its length. So we substitute DC by square root of 3, all divided by 2. And we have to divide the area of triangle ABC by the semi-perimeter S. The semi-perimeter S equals to the perimeter over 2. The perimeter is AB plus AC plus BC. And if we divide the perimeter by 2, we get the semi-perimeter S. So the radius R equals to the square root of 3 plus 1 times square root of 3 divided by 2. And we have to divide it by S. S is AB, and AB is square root of 3 plus 1 plus AC. AC is square root of 6 plus BC. BC equals to 2 units according to what is given in the question, all divided by 2. So the value of this expression, that is actually the area of triangle ABC, it is equals to 2.366 square units divided by S, that is the semi-perimeter of the same triangle, triangle ABC. So the value of this expression, that is actually S, in total it is equals to 3.591. So the radius R equals to 2.366 over 3.591, that is actually 0.6589 units. So in conclusion, we found out that the radius R, the radius that we are looking for of this circle, equals to 0.6589 units. We finished with the first method. In the next step, I will present to you how to find out the radius of this circle according to the second method. First of all, we will define the center of the circle as O. We define the point of tendency of tangent AC with this circle as F. We define the point of tendency of tangent AB with this circle as E. And finally, we define the point of tendency of tangent BC with this circle as D. We join points O and D together by set 9. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We will define the radius of this circle as R, so OD equals to R, it is the radius of the circle. And we have here rule number 1 that we can implement in our drawing according to rule number 1. The tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have here tangent AB, that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM of this circle that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, then this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule number 1. So we can actually implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius OD, that is drawn to point D, that is the point of tendency of tangent BC, with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and D together by set line. OE is the radius of this circle that is equal to R. Again, we can implement rule number 1. The radius OE is drawn to point E, that is the point of tendency of tangent AB with this circle. And therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and F together by set line. OF is the radius of this circle that is equal to R. Here again, we have the radius OF that is drawn to point F. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we'll focus on the common start point C. Actually, you can implement rule number 2. According to rule number 2, the lengths of two tangents from a common start point to a circle are equal. In the drawing we have a circle, and we have also the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this one number 2, they are equal to each other. That is to say PA equals to PB. Can actually implement rule number 2 in our drawing. Why? Because in our drawing, if you focus on the common external point C, from the common external point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say CF equals to CD. Which again, CF equals to CD according to rule number 2. Likewise, we focus on the common external point B. From the common external point B, we have two tangents to the second, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. BD equals to BE according to the same rule, rule number 2. In the next step, we join points O and C together by a straight line. And we join points O and P together by a straight line. And we prove that the green right triangle BOD, this green right triangle BOD, is congruent to the yellow right triangle EOB. So I write it down. I prove that the green right triangle OBD is congruent to the yellow right triangle OBE. So why those two triangles can go into each other? First of all, side OE of the yellow triangle equals to side OD of the green triangle. They are both the radii of the circle, therefore they are equal to each other. So I write it down. Repeat again. Side OD equals to side OE. They are both the radii of the circle, therefore they are equal to each other. In addition, DB or BD equals to BE according to rule number 2. Here BD equals to BE according to rule number 2. Repeat again. Side BD of the green triangle equals to side BE of the yellow triangle according to rule number 2. And finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself is a common side that belongs to both triangles. So OB equals to itself Repeat again. side OB equals to itself, a second side that belongs to both triangles. So if we proved that all the three sides of the yellow triangle EOB are correspondingly equal to all the three sides of the green right triangle ODB. Therefore, we actually proved that the yellow triangle OEB is congruent to the green triangle OBD according to side rule. So I write it down. The yellow triangle EOB is congruent. This is the sign of congruent to the green triangle ABE, triangle OBE, they congruent to each other according to side rule. And from the fact that those two right triangles congruent to each other, we will derive that those two angles must be also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles, must be also equal to each other. So this is angle EBO in the yellow triangle. And it is equal to this angle OBD in the green triangle. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. Okay. So theta plus theta in total equals to 60 degrees. That is to say 2 theta equals to 60 degrees. Here we divide this equation by 2 and finally we get that theta equals to 30 degrees in its size. So actually this is angle theta in the green triangle that is equals to 30 degrees in its size. In the next step I will copy the green right triangle ODB in a new page and we will analyze this green triangle ODB. So actually, this is the green right triangle ODB that I copied from the original drawing. Angle DBO equals to theta, that is 30 degrees. Angle and side OD, this is the radius of the circle, that is equal to R. So in this triangle ODB, tangents 30 degrees equals to OD over BD. OD is R, so it is R over BD. So if we found out that tangents 30 degrees equals to R over BD. Here we multiply this equation by BD and we get that BD times 30 degrees equals to R. We divide this equation by times 30 degrees and finally we get that BD equals to R over times 30 degrees. So this line segment BD equals to R over times 30 degrees in its length. We prove that those two right angles also can go into each other according to side rule. Okay, so we can prove that the orange triangle ODC is congruent to the pink triangle OFC. This is the pink triangle OFC. The orange triangle ODC is congruent to the pink triangle OFC. So why those two triangles can go into each other? First of all, side OF of the pink triangle equals to side OD of the orange triangle. They're above the radii of the circle, therefore they're equal to each other. I will do it quickly because it is the same process as we did in those two right triangles. OF of the pink triangle equals to OD of the orange triangle in addition, CF equals to CD according to rule number 2. Here, CF equals to CD according to rule number 2. And finally, side OC is a common side that belongs to both triangles, so we can write that side OC equals to itself is a common side that belongs to both triangles. OC equals to itself is a common side. So actually prove that all the three sides of the pink triangle FOC are correspondingly equal to all the three sides of the orange triangle ODC. Therefore, we actually proved that those two right triangles can go into each other according to side rule. So I write it down. We proved that the pink triangle OFC is congruent to the orange triangle ODC. and they can work to each other according to side rule. And from the fact that those two right triangles can work to each other, we conclude that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one of those angles is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha in total are equal to 75 degrees here according to what is given as the equation. So 2 alpha equals to 75 degrees. We divide this equation by 2 and finally we get that angle alpha equals to 75 degrees over 2, that is 37.5 degrees. So this is angle alpha that equals to 37.5 degrees in its size. In the next step, I'll copy the orange triangle ODC in the new page and we'll analyze this orange triangle ODC. So actually, this is the orange triangle ODC that I copied from the original domain. Angle DCO is angle alpha that is equal to 37.5 degrees in size, and side OD is the radius of this angle that is equal to R. So in the right triangle ODC, it's very easy to see that tangents 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So the one is found out that tangents 37.5 degrees equals to R over DC. Here we multiply this equation by DC and we get that DC times tangents 37.5 degrees equals to R. Here we divide this equation by tangents 37.5 degrees. And finally we get that DC equals to R over tangents 37.5 degrees. So actually this line segment DC equals to R over tangents 37.5 degrees in its length. So I write it down here that DC equals to R over tangents 37.5 degrees. Side BC equals to BD plus DC. Repeat again, from the domain it is very easy to see that BC equals to BD plus DC. BC is 2 units, according to what is given as the question. So we substitute BC by 2, and it is equals to BD. BD is R over tangent 30 degrees. We substitute BD by R over tangent 30 degrees. Plus DC. DC is R over tangent 37.5 degrees, so we substitute DC by R over tangent 37.5 degrees. So in conclusion, we found out that 2 equals to R over tangent 30 degrees plus R over tangent 37.5 degrees. So 2 equals to, here we'll take R out as a current factor from those two expressions. So what is left from this expression after we took from it R as a current factor? What is left is actually 1 over tangent 30 degrees plus what is left from this expression after we took from it R as a current factor. What is left is actually 1 over tangent 37.5 degrees. So if we found out that 2 equals to R times 1 over tangent 30 degrees plus 1 over tangent 37.5 degrees. So 2 equals to R times 1 over tangent 30 degrees. And 1 over tangent 30 degrees equals to 1.732 plus 1 over tangent 37.5 degrees. 1 over tangent 37.5 degrees equals to 1.3032. So 2 equals to R, and 1.732 plus 1.3032 equals to 3.0352. So if we find out that 2 equals to R times 3.0352, here we divide this equation by 3.0352, and finally we get that R, the radius of the circle that we are looking for, the radius R equals to 2 over 3.0352. This actually equals to 0.6589 units. Okay. So in both methods we found out that the radius of this circle R equals to 0.6589 units. In the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, I found out the radius of this circle. In the drawing, we have a circle that is described by triangle ABC. This is angle ABC that is equal to 60 degrees in its size. This is angle ACB that is equal to 75 degrees in its size. And side BC of this triangle ABC equals to 2 units in its length. Again, our mission to find out the radius of this circle R. So in the first method, we did a construction That is to say, from point C, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. By doing this construction, we created here the right triangle DCB. So I copy the right triangle DCB in the new page and we analyze this right triangle DCB. This is the right triangle DCB to the curve from the original drawing. This right triangle BC equals to 2 and this angle BC equals to 60 degrees according to what is given as the question. And this angle equals to 90 degrees according to construction. So in this right triangle DBC, cosine 60 degrees equals to DB over BC. Cosine 60 degrees is 1/2 is equals to DB over BC, and BC is 2. So we found out that 1/2 equals to BD over 2. We multiply this equation by 2 and finally found out that BD equals to 1 unit in its length. Here, this line segment BD equals to 1 unit in its length. We continue to focus on the right triangle DBC. On the right triangle DBC, sine of 60 degrees equals to DC over BC. Sine of 60 degrees equals to DC over BC. Sine of 60 degrees is equal to 3 over 2, that is equal to DC over BC, and BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally found out that DC equals to the square root of 3 units in its length. Here this line 7 DC equals to the square root of 3 units in its length. So we can write down in the original drawing that this line segment side DC equals to square root of 3 units in its length. In the same right triangle DBC, the sum of the angles must be equal to 180 degrees. The rule that is true in any triangle. So which angles we have inside this right triangle DBC? This is angle, right angle that is equal to 90 degrees, plus this angle that is 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Therefore, the missing angle must be equal to 30 degrees in its size. In order to complete the sum of the angles in this right triangle DBC to 180 degrees, the missing angle must be equal to 30 degrees. So, we know that the big angle ACB equals to 75 degrees in its size. The small angle equals to 30 degrees. So, the big angle minus the small angle must be equal to the missing angle ACD. So angle ACD equals to the big angle that is 75 degrees minus the small angle that is 30 degrees, that is 45 degrees. So angle ACD equals to 45 degrees in its size. Then I copy the right triangle ADC in the new page. We analyze this right triangle ADC. This is the right triangle. This is the right triangle ADC that I copied from the original drawing. In the right triangle ADC, the sum of the angles must be equal to 180 degrees. Which angles we have inside right triangle ADC? This is the missing angle is equal to the missing angle that we found, that is equal to 45 degrees, plus this angle is 90 degrees. 45 degrees plus 90 degrees equals to 135 degrees. So the missing angle must be equal to 45 degrees in its size in order to complete the sum of the angles in this right triangle to 180 degrees. The missing angle here must be equal to 45 degrees. Okay, so those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So those two sides that are located in front of those two equal angles must be equal to each other. That is to say, side AD must be equal to side DC. But we have already found out that DC equals to the square root of 3 units. So we can write here that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units. We derive that AD also equals to the square root of 3 units in its length. Yeah. This is side AD is equal to square root of units in its length. And here also AD equals to square root of units in its length. We continue to focus on this right triangle, triangle ADC. According to the Pythagoras theorem, in the right triangle ADC, AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is equal to 3, therefore DC squared is equal to 3 squared, that is also 3. So in total, AC squared equals to 3 plus 3, that is 6. So AC squared equals to 6. We took out of this equation and finally found out that AC equals to the square root of 6 units in its length. Here, side AC of the right of triangle ABC, side AC of this triangle ABC equals to the square root of 6 units in its length. Then I presented to you rule number 15, and we implemented rule number 15 in our drawing. Okay, so according to rule number 15, the radius of a circle that is described by triangle ABC, the radius R equals to the area of triangle ABC that blocks the circle over S, that is the semi-perimeter of the same triangle, triangle ABC, that blocks the circle. And the semi-perimeter of any triangle is the perimeter over 2. We can actually implement rule number 2 in our drawing. Rule number 15 in our drawing. Why? Because in our drawing we have this circle that is described by this triangle, triangle ABC. Therefore, according to rule number 15, the radius of this circle, we define the radius of this circle R, so the radius R, according to rule number 15, will be equal to the area of this triangle, triangle ABC that blocks this circle over the semi-perimeter of the same triangle, triangle ABC. So, repeat. Now, within drawing, according to rule number 15, the radius of the circle that we are looking for, the radius R, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle is the base of the triangle times the height over 2 over S. S is the semi-perimeter of triangle ABC. We took the base SAB, and the height to the base is DC divided by 2. Again, the base of our triangle ABC is AB, the height to the base is DC divided by 2. All divided by S, that is the semi-perimeter of the same triangle ABC. AB is equal to 3 plus 1, DC is equal to 3 divided by 2. The semi-perimeter of triangle ABC equals to the perimeter, that is AB plus AC plus BC divided by 2. So the radius R equals to the area of triangle ABC, that is square root of 3 plus 1 over square root of 3 over 2 over S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter is square root of 3 plus 1 plus square root of 3 plus 2 over 2. So the value of this expression, that is actually the area of triangle ABC, in total it is equal to 2.366 square units over the semi-perimeter of the same triangle, triangle ABC. The value of this expression, that is the semi-perimeter of the triangle, is 3.591 units, and 2.366 over 3.591 is equals to 0.6589. So if we can find out that the radius R of the circle equals to 0.6589 units. We finished with the first method. Then actually presented to you how to find out the radius of this circle according to the second method. In the second method, we defined The center of this circle is O. We define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent BC with this circle as D. We join points O and D together by straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R, therefore OD equals to R. This is the radius of the circle. And we have here rule number 1. We have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees. That's actually the implementation of rule number 1. Here we join points O and D together by straight line. OE is the radius of this circle that is equal to R. The radius OE is drawn to point E. Therefore, according to rule number 1, this angle was 90 degrees and this angle also equals to 90 degrees. Likewise, we join points O and F. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we implemented rule number 2. Here we focus on point C. From the common standpoint, point C, we have two tangents to this circle, tangent CD and tangent CF. And according to rule number 2, they are equal to each other. CD equals to CF. Here CD equals to CF according to rule number 2. And then we focus on the common standpoint, point B. From the common standpoint, point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. Here, BD equals to BE according to the same rule number 2. Then we join points O and C together by straight line, and join points O and B together by straight line. Then we proved that those two right angles can go into each other. Why those two right angles can go into each other? First of all, EO equals to OD. They are both the radii of the circle, therefore they are equal to each other. In addition, BD equals to BE according to rule number 2. Here BD equals to BE according to rule number 2. And finally, BO is a common side that belongs to both triangles. Therefore, BO equals to itself is a common side that belongs to both triangles. So we actually proved that all the triangles of the right triangle BDO are corresponding equal to all the triangles of the yellow right triangle BOE. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will conclude that those two angles must be also equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. So if one of those angles is theta, then the other angle must be also equal to theta. So theta plus theta, in total, they must be equal to 60 degrees. That is to say, 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that theta equals to 30 degrees. So this is angle theta is equal to 30 degrees in its size. Then I copied the right triangle OBD in a new page and analyze this right triangle OBD. This is the right triangle OBD that I copied from the original drawing. This is angle theta that is equal to 30 degrees in its size. And side OD is the radius of the circle that is equal to R. So in this right triangle OBD, tan 30 degrees equals to OD over BD. Okay? Tan 30 degrees equals to OD over BD. OD is R, so it is R over BD. So tan 30 degrees equals to R over BD. We multiplied this equation by BD and found out that BD times tan 30 degrees equals to R. Then we divided this equation by tan 30 degrees and finally found out that BD equals to R over tan 30 degrees. Here, this line segment BD equals to R over tan 30 degrees in its length. Then we proved that those two right triangles also can go into each other according to side rule. A bit quickly on the proof. OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. CF equals to CD according to rule number 2. Here CF equals to CD. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. So I shall prove that all the three sides of the pinic right triangle OFC are correspondingly equal to all the three sides of the orange triangle ODC. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will conclude that those two angles must be also equal to each other according to the rule that corresponding angles can go into triangles are equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha in total is equal to 75 degrees. That is to say, alpha plus alpha is 2 alpha, so 2 alpha equals to 75 degrees. Here we have 2 alpha equals to 75 degrees. Here we divided this equation by 2 and finally found out that alpha equals to 37.5 degrees. So this is angle alpha that is equal to 37.5 degrees. Then I copied the orange right triangle ODC in a new page and analyze this orange right triangle ODC. This is the orange right triangle ODC that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees, and side OD in the radius of the circle that is equal to R. So in the right triangle ODC, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. Times 37.5 degrees equals to R over DC. We multiply this equation by DC and finally found out that R equals to DC times 37.5 degrees. Here we divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. Here, this side DC equals to R over times 37.5 degrees. BC, from the drawing it is very easy to see that BC equals to BD plus DC. Okay, BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC is 2, BD is R over times 30 degrees, and DC is R over times 37.5 degrees. So in conclusion, found out the 2 equals to R over times 30 degrees plus R over times 37.5 degrees. Here we took out R as a second factor from those two expressions. So we found out that 2 equals to R, and inside the brackets we left only with R over times 30 degrees plus R over times 37.5 degrees. So 2 equals to R, and 1 over times 30 degrees is 1.732 plus 1 over times 37.5 degrees is 1.3032. So 2 equals to R, and 1.732 plus 1.3032 equals to 3.0352. So in conclusion, found out that 2 equals to R times 3.0352. We divided this equation by 3.0352 and finally found out that the radius R that we are looking for, the radius R equals to 2.2 over 3.0352. That is actually 0.6589 units. So actually in both methods we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.